Okay, so some of have attended my previous sessions also. Recording is there, Gopi. It's in the YouTube. Okay. So go to the data section of Analytics Vidya. Okay. Subscribe to that and you can find it in the uploaded videos. So hypothesis testing video is already uploaded. Okay. So I'll just share this link once again and someone can try posting this in the YouTube as well so that those participants can also download these. There is one notebook only, okay? And as we have already mentioned that this is going to be more of a three-part series. So in the first part today, I'm going to discuss about basic text processing, what all data cleaning, processing, feature extraction, feature engineering, everything. Basically converting your unstructured data, which is your textual data is always considered to be unstructured, into a structured format. We'll construct features out of it. Once we have the features, but there are different strategies to convert your textual data into a structured format. Basically, different feature extraction or strategies are there. Okay. So one of those strategies is bag of words model. Okay, which is what we are going to do today. So we'll construct the features by using bag of words and then finally apply some machine learning algorithms. So here, I don't intend to create a very sophisticated model, but you can try out using XGBoost and whatsoever is your favorite algorithm. But in principle, how to bind all these concepts into an end-to-end project. So that is what is the main intention of coming up with this session. And then there are several variations. I'll tell you what all variations are possible at what all points, I would say. So you can try out all those variations. There could be variations of feature extractors, variations of different machine learning models, variations of cross-validation techniques, variations of grid search, hyperparameter tuning. So all these things which we are going to do, variations of even pipeline end-to-end, okay? So all those experimentations you can do with this notebook once you have that, okay? So enough said, let's get started immediately, okay? And I think, sorry, just a second. Okay, perfect. So let me share my screen once again. I think we are warmed up by now. Yes. Good. Okay, so before I start with this, let me give a brief idea about the domain. So as I said, this is going to be a three-part series. So in this first part, basic text processing, feature extraction, feature building, and machine learning models. And then in the next part, what I'm going to discuss is instead of bag of words model, what other type of models can be done. Those deep learning models like word-to-vec, global vector models, Elmo is there, which is again more of a language modeling. And then how do you use word-to-vec models and glove models to get your word embeddings? So that's all deep learning applied to NLP. Okay, that would be the second part. And then we'll also create some deep learning models for doing the same project. Okay, so the project would remain the same, data set would remain the same, but you will at least get a comparison between how a machine learning project with respect to what textual data would go and a deep learning project with the same textual data would go, right? So that clarity and that difference you can easily make out. This light. Just trying to find out a good angle. Okay, so that's one thing. And in the third part, what I'm going to do is take the deployment. So whatever model I'm going to create, at least will be deploying in a local machine and on the cloud. And we'll actually create an end-to-end Flask application and deploy this on a Docker image. That Docker image will be uploaded and that will be hosted on a cloud server and will be accessible to everyone on the globe. Okay, so that's the three-part series I am planning. Okay, so good to go. Data set is already uploaded. There are a lot of pre-processing which needs to be done. I think I'll just show you this tweets.csv file. And initial code for loading and all that is there because I don't want to spend time in discussing all that stuff. So the initial code is all there. What I'm expecting is your machine should already have natural language toolkit NLTK pre-installed. Okay, so maybe I can start from the start. And before I get to this, there are a couple of things. So when I say natural language processing, basically I'm not building a model. Okay, so NLP is just to make your raw text ready for model building. Okay, so your raw text is what you can see. Your raw text will look like this. So this is not yet ready. This is not up to the machine capability to learn anything from it. Okay, machine only knows zeros and ones. So we have to process this text so that it is legible to a machine. Okay. So NLP is natural language processing. So basically we have to process the raw text to make it ready for model building. So the end project will be having some NLP concept plus model building. And this model building can comprise of ML model or basically your deep learning model that you can choose at the end. Okay, depending on what task you want to achieve after you have processed the data. Okay, now, what are the several tasks? Okay, so these are the several applications I have given quickly. Okay, and then we talk about text classification, which is the project which we are discussing right now. You can also do a text summarization. Now, there are two kind of techniques, abstractive, extractive, and so on. Basically, it's like a 40-page document you want to summarize in one paragraph. So you want to create a model which can summarize a 40-page document in one paragraph. That can be done. Named entity recognition. Basically, in any news article, there will be named entities like name of a person, name of the organization, geopolitical entities, name of cities, name of rivers. So your model can extract all these proper nouns, and that will help us to find appropriate context, a topic for that particular news article. So that is one potential application of named entity recognition. Part of speech tagging. So for each word, you can assign a part of speech, whether it is a noun or adjective or adverb and so on. So part of speech tagging is actually used behind the scenes in the named entity recognition. Fine. Topic modeling. So again, if you go to Google, news.google.com, you will see several news items clubbed together. You will see buckets of news. Okay, in one bucket, you will find several news articles from different sources, but they are grouped because they are referring to the same incident. Okay, and then you find another bucket of news, okay, in which there are several news articles coming from various sources, various media houses, you can say, okay, but they are reporting the same news item altogether. So some topic is being extracted, right, from each of those news article, and those topics are, compared, and a similarity is found, and then similar news items are clubbed together. So no one is manually clubbing them together. Maybe I can quickly show you. Okay, so news.google.com, if you just go there, you can see these 3-4 news items. They are clubbed together as one. Okay, then another bucket of news items, you can see another bucket. So you click on any tab, maybe. Okay, you can see buckets of news articles. So how is that working? Okay, how is that working? Who is clubbing them together? So there is a algorithm behind the scenes. Now these 3-4 news articles are grouped together. These 4 are grouped together. That is exactly going behind the scenes when I say topic modeling. So topic modeling is another potential application. So maybe in the subsequent sessions, if there is a request from your side, I can take one of these applications further, topic modeling especially. So these are the different algorithms normally used for topic modeling. So there are already DataHour sessions on latent Dirichlet allocation. I remember 3 weeks back. You can find the recordings in the YouTube. Fine. So an example of the text classification is email or a SMS message classifier, whether it is a spam or not spam. Okay, you can specify, classify a WhatsApp image or a SMS message, email message into these 2 classes. So it's a simple text classification example, or any movie review or a product review, anything that you can classify as positive, neutral, or negative, or even Twitter sentiment analysis. That is a project which we are discussing currently. Hate speech recognition. So again, Twitter or elsewhere. Okay. So these are the kind of, applications you can work on. Chatbot is another, interesting application area of NLP. These are the different libraries which are normally used, NLTK. So these need to be pre-installed in the system before you can run these code. So NLTK typically comes pre-installed along with Anaconda. You might have to download the corpus, NLTK.download. Okay. That's a one-time configuration, but you can do that. So NLTK, that's the base framework of natural language processing available within the Anaconda ecosystem or the Python ecosystem, you can say very well. Spacey is a completely different and a new framework, more advanced, you can say slightly. Okay. So when I say framework, it's like you are comparing TensorFlow with Python. These are two different frameworks of creating deep learning models, right? Whereas Keras is a wrapper over TensorFlow or Theano, maybe. So the same thing is happening. Text blob is a wrapper. So behind the scenes, NLTK functions are running. So 20 lines of NLTK code is one line in text blob. That's how, and that's what I mean by saying it's a wrapper. GenSim again contains lots of pre-trained models. So we'll talk more about GenSim in the next session. We'll be talking about word-to-vec model, embeddings. Okay, all sort of word embeddings are there. So those things are available in GenSim. Both pre-trained models as well as untrained model architectures are there. You can import those model architecture and retrain it on your own data set, right? Okay, so some common terms which one has to be very familiar. I just want to take some time in this. So corpus is the collection of documents. What is a document? One tweet, for example, here, one tweet will be considered as one document. Each tweet will be considered as one document. So single data point in NLP is called as document. Document is your single data point. So it could be your individual messages, emails, tweets, reviews, news articles, or entire 50-page document. But each document, okay, will be one data point in NLP. Is that clear? So if I have a collection of all these documents, what I get in hand is corpus. Corpus is essentially collection of documents, because I'll be using these terms quite frequently in my technical part of the code delivery, because as I told you, I do not have slides here. So this is the only notes I created to save some time, you can say. So document will contain several paragraphs, and these paragraphs will contain several lines, and each line will contain several words. So your machine is not bothered about the structure of the document, okay, whether it contains a collection of words or it contains sentences, which are collection of words, doesn't matter, okay. All it knows is document will be collection of words, okay. Now the sequence of words will have some meaning, some context, and that is what I meant by saying semantically. And syntactically means the machine should be able to understand the grammar. So this is more of NLU, natural language understanding. The machine should be able to understand the syntax, basically the grammar, the structure of the sentence, and semantic means context. Okay, context, the correct context of a word, okay, should be able to, the machine should be able to figure out. So your model should take care of these, basically. Perfect. So these two words are very clear. So corpus is a collection of documents. Document will be collection of paragraphs, sentences. Now these things, as I said, will not make any sense to the machine. To the machine, this is the structure which makes sense. So machine only knows corpus, which is your entire data set, documents, which is a single data point, and every data point will be collection of individual words. That's it. Now, there is one more thing, concept called as token. So when you are breaking a document into individual words, those individual words are called as tokens. Okay. So you have to break a document into small chunks. Typically, these chunks are called as tokens. Now, one token could contain a single word or two words or three words, I mean, or more even. So if each token is containing a single word, we call it as unigram token. And if the tokens are collection of two words, it's a bigram token. And if the token contains three words, it's a trigram token. Basically, the value of n well defined. So this also we will see n-gram tokening, okay, tokenization. Finally, vocabulary. Vocabulary will be collection of all the tokens from the entire corpus. So each document will have tokens. For now, just imagine token is nothing but individual words in the document. So I collect all the words from my entire document and put it in a list. That list will be called as my corpus. It is as simple as that. But these are unique tokens. So repetitive words are ignored. Simple. Typically, we use either as a list or as a dictionary, and there is a special type of data type called as counter from the collections package. So these are the three most common ways you can represent, or rather you can encode, or maybe you can hold the tokens. Okay. So the data type could be a list or a dictionary or a counter. So it depends on what further processing you would be doing. Okay. So we prefer to either make it as a list or a dictionary or even a counter. So it depends. In this project, we'll see what data type we are going to use for vocabulary. Right? But finally, it is containing all the unique tokens from all the documents. So if it is a dictionary, for example, or even a counter is a special type of dictionary. Okay. Counter is a special type of dictionary. So if it is a dictionary or counter, then obviously dictionary is collection of key value pairs, correct? So what will be the key? The key will be the actual word, and the value will be the frequency of the word. Basically, how many times that word is appearing in the entire corpus. Okay. So that is the word frequency. So it will be a key value pair. There is one fantastic link. I'm just posting this in the chat box. You can just refer. These contain additional tutorials for text processing within scikit-learn. This is freely available. You can just check that out. Okay, fine. Let's start with the project. So the project that I have in hand, and there are already 6 questions. Okay, let me answer a few of them. Okay, so there is one question.
Prashant, please, can we take that up at last? We are already 7:30.
Okay. Fine. Okay, so let me start this. Okay. So this is how your data set looks. Basically, there are 3 columns. One is the ID column, which is nothing but the ID of the row. Label is 0 or 1, and 0 refers to a positive sentiment, and 1 is referring to a negative sentiment. Simple. So you can see very well that your data contains hashtags. There are some URLs are there, and then there will be smileys. These are special characters. Okay. User mentions also, you will get @ something. You will get some numbers, dollar symbols, Instagram links, and number of things are there. So basically, we know that these things are not going to determine the sentiment, right? The hashtag usually doesn't. So, or if it is, really important, you can at least get rid of the hashtag. I mean, you can still retain the word. So I'm not going to delete the entire hashtag. Rather, I'll retain the word and just delete the hashtag as such. Okay, so that pre-processing I'll be doing. Fine. Definitely the URL will not determine the sentiment, so we'll delete all the URLs. Numbers cannot determine the sentiment, so I will delete all the numbers. And the same, the user mentions also will not have any. And then there are some domain specific stopwords, we can delete them, like tweet, retweet. Okay, some of these. So basically, what are these reviews all about? These are, some product reviews. You can say mobile phone reviews, and people are talking about some features in some mobile phones that they like or they do not like. Simple, whatever feature they are liking in iPhone or Sony Xperia, you can see these words. And so basically, it's all about mobile phone reviews, different brands, different models, different accessories. It is just a collection of that. Okay, simple. So basically, whatever product review it is, whether they are liking that particular product or not. Here, the product is not narrowed. Okay, the product is not narrowed. It's all a mixed bag. So I think we are good till here. Just checking for the null values. So there are no null values. So the data is not having any null values. What I'm going to do is I'm dropping the ID column. I think that was already dropped. Yeah, so I accidentally dropped it. Anyway, I just you will not get that error. Okay. You run this code once again, you will get this error. So I have dropped the ID. Now I have got only label and the raw tweet here. Fine. Just checking for the class balance, clearly shows that 75% of the tweets have a label 0 and another 25% have the tweets label as 1. So it's not a very much balanced data set. 75-25 is the slight imbalance. It is not that very imbalanced also, frankly. So you don't have to, worry much about the class imbalance in this case. And some basic techniques of handling the class imbalance we will take during modeling. We'll not do any processing, any additional step to make it balanced. Is that very clear? Okay, because this is not so concerning imbalanced. Concerning imbalance means if one class is 95%, other class is only 5%, or one class is 98%, other class is only 2%. That's concerning. Okay, this 75-25 is very much, you would find in any real world scenario. So that's why I'm not going to spend any time talking about any class imbalance handling. Okay, the only basic technique that is available to us, we'll use that. I'm just plotting the same thing. So nothing. Yeah. Okay, so now I'm pulling out one of the tweets here and importing the regular expressions module. So that's a package RE, regular expressions. Some standard regular expressions are there. So you can use these regular expressions. I really don't want to spend time in explaining these regular expressions. There are other sessions already done on all these text-based processing, which was given to us as prerequisite. Fine. So I'll just go ahead and just run the code. I'll focus more on the model building part, right? So what this is going to do is, it is going to substitute all the apostrophe s. Can you see this apostrophe s will be substituted as space and s. Okay, so this is the regular expression, how I'm going to identify the apostrophe s, and all the apostrophe s will be replaced with a space followed by s. Simple. Let me apply it on a single tweet, and then we'll use that line of code and construct a function. Fine. Here, you can see one of the tweet has got user mentions @Apple, okay, or maybe something more. So what I'm going to do is we'll retain the alphabets and digits only and get rid of any other smileys, any other symbols. So now you can see that sign is gone. In fact, the entire user is gone. Okay, that's very fine. Now we want to remove the hashtags. So you can see there are hashtags here and here. So I'm removing the hashtag. So basically you are just substituting the hashtag with nothing. Essentially it's removing. Okay. Then you are searching for this pattern HTTP and anything that follows. That will be able to identify the URLs, right? So you can use that to identify the URLs. So here we have the HTTP. Once I run that entire URL is gone. Finally, I want to only retain alphabets. I want to get rid of all sort of punctuations, special characters, digits, and every other nonsense. Okay? So now you can see this is my original 25th tweet, and after using this kind of regular expression, all those exotic things are replaced with a space. So you will get a lot of spaces. We can handle that easily. So now you can see you have only alphabets. Fine. Somehow there is a URL which got skipped. That anyway we will handle one by one. Okay. So there is a concept called as stopwords. Okay. So what is stopwords? Basically, the most common English stopwords like you, me, my, a, and the, these kind of words, if you see, they are neutral words. Okay. They cannot determine whether a tweet will be having a positive sentiment or a negative sentiment. They are not discriminatory words. That's the correct word. They cannot discriminate between a positive and a negative tweet, right? So what I want to do is I want to get rid of all these words, okay, entering into my vocabulary. Please understand once again. I want to get rid of all these words from the tweets. These words are would be present in the tweets, right? So I want to get rid of all these words from the tweets so that they do not enter my vocabulary. So my vocabulary will be neat and clean and containing only those words which are discriminatory, which are informative, which are important words for the model, right? Because these words are not going to be very informative. They are only going to be, noise. They are just noise for the model otherwise, right? So that is the idea. And that's the reason we call them as stop words, because we want to stop these words from entering into my model. That is why they are called as stop words. Fine. So let's pull out all the stop words from the NLTK library, and you can see these are the stop words. I have just printed them. So in natural language toolkit, you will get 179 stop words. You can see the length. And similarly, there is a scikit-learn library, which also has another, how much? 318 stop words. So what I'm going to do is I'll just join them both. Okay. So union is where I'm joining them, and just out of curiosity, I'm just trying to find out how many stop words are common, right, between this list and this list. Okay, how many of them are common? For that, I converted them into sets and then just printing an intersection. You can see these are the common stop words in both the packages. Scikit-learn has a list of stop words which are 318 in number. Your NLTK has built-in stop words, which is 179 in number. These are the common ones, and I'll just combine them both. Okay. So after combining, this is what I get. And maybe if you want to see the length of the combined stop words, you can just try out this. 378 stop words in total are common. Fine. Sorry, no. Common is 119, but 378 is combined. Right? So there is a concept called as normalization, word normalization. There is case normalization, where you convert all the words into either uppercase or lowercase. That is case normalization. And word normalization is basically you get rid of the various inflectional forms of the words. So for example, you have go and goes both. Now, if you think that go is a useful word for your model, then its future tense, its other, inflectional forms, past tense, went, let's say. Now, they are not going to add any new information. So go, went, goes, gone. Let's say all four words, they are referring to the same action. They are all referring to the same action. So ultimately, if there is a sentiment attached to this word, all the four words would have the same sentiment at the end of the day, right? Or there is a word called as river. Rivers is not going to change the sentiment. So river and rivers are supposed to be interpreted as one word. So what I'm going to do by stemming and lemmatization is, I want to get rid of these various inflectional forms of these words. Okay, so go, went, gone, they will all convert into a base word called as go. That is what lemmatization does. Stemming only gets rid of the prefixes and suffixes mostly. So for example, potato and potatoes. Okay, so ending es will be stripped by stemming. So stemming comes with set of rules. Okay, it's faster because it comes with set of rules, but many times it messes up your words. I mean, the words can convert into non-dictionary words also. Whereas lemmatization will import an entire English dictionary into memory and make sure that most of the lemmatized words are actually dictionary words. Okay, so if they can be reduced, fine. So there are different stemmers and lemmatizers. So Porter stemmer, Snowball stemmer, WordNet lematizer, and number of stemmers and lemmatizers are available. You can just open ChatGPT and ask, give me the list of stemmers and lemmatizers available in NLTK. You'll get a complete list very easily. Okay, or go to Google and just search stemmers and lemmatizers easily. Fine. So here I'm just going to focus on one of them, which is WordNet lematizer. Okay. And you can see that this is my tweet. After splitting, what I've got is the individual tokens. So these are my individual tokens, right? These are my individual tokens. What I've done here is used this simple for loop to pick up each token in one iteration and lemmatize it. And after lemmatization, I am just concatenating with a blank string, you can say, okay? And I'm just printing it after lemmatization. So you can see that followers, this followers has become follow. That is the result of lemmatization. Okay. I think most of the other words are same, but this is one word which changed. And what I have also done is a case normalization. So I've converted everything into lowercase and called my lemmatize function. So this is going to, get rid of the various inflectional forms of these words, convert into their base words. Okay. So all plurals will be converted into singular and so on. Fine. So yeah, this works. You can install this contractions package. Now, what are contractions? So, for example, it's time. So word like didn't, wouldn't, can't, okay, doesn't, I would have, you will write as I apostrophe VE. These are all called as contractions. So mostly because of the word limits, people tend to use these short forms, right? So you can easily just Google what are contractions available, what contractions are available in, this package. You will get to see all these contractions. So there is a way that you can expand those contractions. Okay. So for example, what I'm trying to say is I apostrophe VE. Now this is a short form of saying I would have or I have, for example, I have, or ILL, so I will or I shall, anything. So these are the contractions and these are the expanded forms. So you can use this particular package and expand all the word contractions. So that is the idea. So I've already installed it. Okay, so let me just go ahead and quickly open this. Okay, I'm running this in a my kernel. Let me see if there are any other questions. Just wait. I'll share my screen once again. Don't worry. Okay, sharing my screen again. I think this will work now. Yeah, this works. So these are the contractions I was talking about. Okay, these are the contractions, and sorry, I have to run this one. So the other notebook is the one which I have shared. So let me just check. This also works without That works. You can see this works. So what I've done is I collected all these 7-8 steps and a cleaner function. Okay. So now you know, right, each of these. So this is going to substitute your apostrophe s as space and is, and then this is going to remove the hashtags. This is going to remove the user mentions, @ and everything else. This is going to remove the URLs. It's not a foolproof method of you removing the URLs. You can easily get some more regular expressions elsewhere. This will expand all the contractions, just like what it did here. Okay. What else? Then you are retaining only alphabets. That's it. Small and okay. And you are see there is a caret operator here. So this is negation. So anything which is not alphabet, either A to Z small or A to Z caps, anything which is not, this is a negation operator. Anything which is not an alphabet, delete it with a white space or substitute it with a white space. So that way you are getting rid of all the other things other than alphabets and other than alphabets. Then finally converting everything into lowercase and stripping all the extra spaces before, after, in between. Okay. So this is how you get your new text. Fine. And then you are tokenizing those clean text. Okay. So you are running on this, right? So dot split will convert it into a list of words, and that list you are iterating over that list. So each word will be lemmatized and a new cleaned text would be constructed. So each word would be lemmatized and joined or concatenated with this new string that you are creating, right? So finally, this function returns your clean text. Simple. Let me apply this function and get a list of clean tweets. So this is your entire tweets. So what I'll do is I'll just print the top 5 tweets, okay, instead of printing everything. So I've applied on everything, but I have just printed the top 5. So you can see very neat and clean now. Very neat and clean. Perfect. Pretty neat and clean. There are some additional spaces, but that's okay. We can take care of that easily. So you can pull down any of their tweets and just check. Okay. This is how your original tweet looked, the 1500th tweet, and this is how the 1500th cleaned tweet looks like, right? You can see the difference here radically. Okay. You see, this was probably a hyperlink pic.twitter.com, but since it did not start with HTTPS, it escaped to my regex function. And so it is now a part of your clean tweet also, which will now enter my corpus as well. Vocabulary as well. Okay. But there are ways we can still filter these guys out. Okay. So don't worry. Okay. So what I'm going to do is, after applying, I have all my clean tweets in this variable. I'm going to append it to my original data frame. Okay. So now you have the original tweet, and this is clean tweet without the stopwords done. Okay. Because if you see, my cleaner function did not implement the stopwords. I want to see what happens with and without stopwords. So right now, let me have something as the original tweet and the cleaned version without the stopwords removed. Okay. Now let's see some data visualization. Okay. Some data visualization. Okay. I think I have just turned it off. Hope that is fine with everyone. Okay. So what I want to do now is visualize the top 25 most common words in this tweets data set. Okay. I want to see what users are talking about. Okay. I want to see what are the top things the users are talking about. Fine. So I just created an empty list here. And then what did I do? Splitting each of those tweets. So each tweet will be a statement, right? So dot split will convert this into a list of tokens, individual words. Okay, so it breaks into individual words and those list of tokens basically. So list of words. Now that list gets, so each word from that list is now appended to the main list, this empty list, by using the extend function. So what I said is each word from every tokenized tweet will be appended here. Listen to me once again. Each word is going to be appended to the list here. Okay. There is a difference between extend function and append function. Although I'm using extend here, but in my explanation, I use the word append. If it had been actually append, then this tokenized tweet as it is. So what do you mean by a tokenized tweet? Okay, you can take any of these tweets. For example, this is a tweet. Let me tokenize and show you. What I'm doing is just split. So this is my tokenized tweet. So this tokenized tweet will simply get dumped into the parent list. That is what I do not want. I do not want my parent list to have a list of words once again. Rather, what I want is my final list to contain the words directly rather than the words as a list, which is why I'm using the extend function. Okay, so if you're still not very confident about the extend function, please read any Python tutorial on extend and append. You will see that difference. So finally, let me run this, and what I get is 34,348 words are present in 7,920 tweets. Did you notice that number? 7,920. How many of you noticed that number? 7,920 entries are there. So all in all, you have 7,920 tweets, which contain now 34,000 something words, 34,348 words. What I'm going to do is just plot a frequency table. So this frequency table is being generated by natural language toolkit function called as frequency distribution. Okay. And then I'm simply plotting. These are standard plotting functions. What do you see here? What do you see here? This is least informative. I would say this is crap. This is completely useless. Why? Because I cannot see any meaningful words in this, right? The words like to, my, I mean, what do I make out of these kind of words? Come on. These are such generic words. Now, what do I do with these 3 dots and 1 dot, right? They are all useless. Even this me and with. Probably the only useful words that I can see, meaningful words that, okay, people are talking about iPhone, people are talking about Apple, people are talking about Samsung, again, iPhone, Apple in a different case here. Okay, nothing much, right? So if you noticed, this plot was constructed for original tweets. Did you see the code here? This is data tweet. This plot was constructed for original tweets without cleaning. Now, all the guys who have access to this code, please write down or rather rewrite this code, okay, and plot for the cleaned tweets. You will see that difference. Okay, so write the code. I'll take half an hour more. So if you are in a hurry, you guys can leave. And come back with the recordings. I mean, the recordings will be uploaded, so you can watch the remaining part in the recording. Okay, I'll take easily half an hour more. Fine. So write the code for plotting the cleaned tweets. So let's see, you guys would be able to do. I'm pretty sure. Okay, all you have to do is just copy here probably, and instead of using the raw tweets, use your clean tweets. This one. I'll wait here for half a minute. I think that should be fair enough time. Okay. So, I mean, it's very difficult to learn anything in 1 hour. One has to spend time, and people who have been attending my sessions know the data for me goes for even 2-3 hours also. Not joking, but seriously, my last data hour went for 2.5 hours. So I won't leave you until I am satisfied. I won't leave you until I am satisfied that you have really learned something. Yes, guys, have you reached there? I'm also doing simultaneously, don't worry. Okay, perfect. So I'm done. It was all just a copy paste stuff. Okay, the only difference was instead of normal tweets, I just changed it to clean tweets. It's exactly the same copy paste code. Guys who joined late, maybe I can share the link for the GitHub once again so that you can download. Okay, and catch up. Right. Let me run this. So I'm just printing the first 50 words after cleaning. Okay. Of course, this is just to make sure that what I have is the right data here. And here you can see unclean tweets contain all sort of, surprise elements. Okay. This is your unclean tweets and this is your clean tweets. And let's see how much this number comes to. So you see 34,000 comes down to 15,000. Why are we bothered about that number? Any idea? Any idea? Why are we bothered about that number? Just read this part. That is the answer. Okay. Forget about everything else. Why are we bothered about that number? This is the reason here. Clearly, I've mentioned that the size of the vocabulary means how many words are finally going to enter your vocabulary. That is the size of the vocabulary. Okay. How many words are finally going to be present in your vocabulary? That is the size of the vocabulary. That will determine the size of feature. Essentially, what I'm trying to say is every single word in that vocabulary will become a feature. Every single word in that vocabulary will become a feature. So I do not want absolutely any nonsense word to be a part of that vocabulary. So that is why I'm so careful about data cleaning, right? You have to spend hours, that's worth. Okay. Good. What else? So this vocabulary will be used to make your corpus structured finally, and the structured corpus will look like the number of document times the number of words. So M cross N. So we'll talk about that documentum matrix. It's too early to discuss that. So finally, I'm getting 15,981. So is everyone getting a similar number? So do you think even 15,000 or roughly 16,000 words, rather let me translate it to saying, if I say that this data set is going to be having 16,000 features, can you imagine we are going to have 16,000 features? You are going to make a machine learning model for the first time with 16,000 features. Do you think it is awesome or awful? I mean, it depends in what context you are talking about. Okay. So this is definitely not awesome. Let me tell you, if you think that more features is better, definitely you are screwing up your machine with 16,000, features. Your machine can easily get confused. Okay, so that is the job of the data scientist, to figure out the top features from that pool of 16,000, because you still know that not all of that 16,000 features is informative, right? So that is the experience which companies are looking for when they say, I need a guy with 3 to 4 years of experience. That experience tells them, okay, out of that 16,000, only 600 or maybe 1,000 are really informative. But which ones, that experienced guy will be able to tell. For the guys who are starting new, there are ways that you can find out that 1,000 best features, okay? Not manually, but by using a code, which is what I am going to tell you. Okay. Reduce the dimensionality, Mayur. Yes, of course, we can even do that. That is what also we will try it out. Okay. Stay tuned. So this is the frequency distribution. And now what I want to do is, okay, what I want to do is, I want to continue this exercise and let us first change my cleaner function to include stopwords. Can you do that? Can you do that? There is a code which applies stopwords, correct? Somewhere there is a code which applies the stopwords. Somewhere, is it there? No. Okay, don't worry. So what we will do is we will rewrite this cleaner function. We'll rewrite this cleaner function to include the stopwords. Why am I doing that? Why am I doing that? Answer is very simple, because now I want to see how does this plot change after applying the stopwords, correct? Yes, does that make sense? Now you see, before we even do that, okay, now you see more useful words would be there, like iPhone, Apple. Okay, these kind of words we still need to get rid of. Okay, these are going to be my stop words. Okay, these are going to be my stop words. But at least I have got more useful words. Samsung, Twitter, phone, follow, Sony. Sony never emerged in the previous plot. This time Sony also came. Okay, what else? But largely this is all, stop words for me. Not so once I get rid of these stop words, I'll find something more informative coming up. Make sense? Are you following me? Right? So I want to get rid of all these nonsense words, and more meaningful words will emerge in the plot. You see? So that is the intention. So let's apply stop words and we'll do the replot once again. Okay. See, model building is one last part. Before that, we need to make sure that we have the right data to build the model. So don't worry, model building is no big deal, but getting your data right and then in the right shape is very, very important. Always. Okay. So please change that cleaner function. Okay. Just copy that cleaner function. I think I have already copied that cleaner function. Just pasted it. Now I want to include that stop words. Okay. I want to include that stop word removal in this cleaner function. Fine. So just give a thought. Give a thought. What I'm going to do is simply copy. Where is my stop words? Here. So this is my combined stop words. Okay. This is my list of combined stop words. Okay. So can I use this combined stop words and modify my cleaner function in a way that will do the So let me just copy this. Okay, somewhere here I will paste. So where do I apply my stop words? So this is my combined stop words, right? Which I'm going to apply, but how? So let me write down a simple list comprehension. Okay, new text is equal to, okay, new text is equal to Okay, let me check out some of the messages in the chat box in the meantime. You guys try how you can do that. Oh, Himanshu, thank you so much. Thank you. Thank you for your kind words. Okay. Fine. So next text, a new text, sorry. So what I'm going to do is use a list comprehension. So what I'm going to say is for token in, so I'm going to split this guy in this one, whatever has been processed here, dot split. So what I get is a list of tokens, correct? And for each token in that list, I'm going to run my for loop. Simple. I want to check if that token is not in my combined stop words, my dear, then please pull out that token for me and save it in this list comprehension. Awesome. This is what we wanted to do. Okay, I'll just paste this line of code in the chat box. You can implement it at your end and see if that works. So let me run this. This is error free. Now I want to apply this. So apply, okay, apply code also is also there. So you see, code reusability is very important. Okay, you should be able to reuse your codes very easily. Okay, so where am I applying? We are applying it here. Okay, let me see. We are applying using a for loop. Now this is not a very good way of doing coding. I'll tell you very frankly. This looks amateurish. See, we are applying the function here. Did you see? For each tweet, I am applying that cleaner function. This is my cleaner function. Okay. So I'm applying that function using a for loop. It is a very amateurish way of applying the cleaner function onto a data frame. What is a more pro way? Okay, let's write down a pro. So I'll not copy paste that function, and make sure that you change the name of this function not to get confused. So what I'll say is this is with stop words. Okay, so this is tweet cleaner with stop words. Okay. Once again, this is tweets cleaner with stop words. That is the name I'm using. So do not get confused. Not all the code is being pasted. So only those selective lines which are being changed, that is what I'm pasting. Okay. So I'm not pasting the entire code. That doesn't make sense. So only this line I have pasted, and you know where to put it. Okay. Please. So make sure that this is with stop words. And now I'm going to apply this in a more pro way. Okay. This will look as if you are really a data scientist. Okay. Fine. Data, and then I have tweet, then apply function. Okay, I'm going to copy the name of this function. That's it. This is the best way of applying a function into a column of a data frame. Once again, I repeat, this is the best way. A pro way means Pythonic. Yes, absolutely. Pro Pythonic way. See, this was also a Pythonic code, but that was amateurish Python code. Okay. This is more of a, pro level Python code. So that's fine. Anyway, so I want to save this. So let's call it as cleaned tweets. And we'll do one last thing. I'll convert that into a list. And let me print some of these tweets. Let's say I'll print the top 10 and see how it goes. It work. Test object has no attribute. Let me check what went wrong. So if I am getting this as a list, Okay, perfect. So there is one change you need to make. I got the reason. Can you see the problem is in this line? Perfect. So there is one more thing that I need to change is delete this split. Delete this split. Okay, delete this split. That should work. Wow. So that worked. So let me paste this entire function here in the chat box. Okay, the entire function. So this was the other change. Here you had a split. Now this was already a list, and list does not have the split method. That is exactly the error message you had got. See, this was already a list. No, this was already a list. You are using a list comprehension, correct? You are using a list comprehension. So this is already a list, and you were doing a dot split on that list. So list data type does not have the split method. You guys remember? That was the exact error message. And from there, we got the hint that I slightly needed to modify this. So this is how the first 10 tweets look like. Perfect. All I have to do is now push it back to my data frame. Okay. So how do I push it back to the data frame? Let's call it as, let's dot columns. Let's see what are the column names already. So this is my column name. I'll just copy this column name and modify that slightly. So clean tweets with stopwords. With stopwords means after applying stopwords. Okay. That is equal to my clean tweets here. Now let's see the data dot head. Perfect. So I've got my data set here. Okay. Yes, I'll update the code in the GitHub. Don't worry. After the end of the session, even if you are not able to continue, that's fine. I'll update this. Okay. You can download the updated code before the next session, whenever it happens, probably somewhere in the first week of Jan. Tentatively 4th, 5th, I'm planning, but we'll see the availability. Okay. So this is what I get. Okay. This is how I applied. And this is how you can check. This worked. Okay. And next. So we are ready. So all I have to do is just copy paste this code once again. Okay. I'll just remember one thing. This has to be clean tweets with stopwords. Okay. So otherwise you will still plot the previous data. Okay. So that code is done. And then I'll need the frequency distribution. Need the frequency distribution. Right. So let me. Wow. So what do you see now? What do you see now? You see more meaningful words coming up, more number of meaningful words coming up. You see? You have got love, iPad, follow, Twitter never appeared, Android never appeared. Okay, photo. People are talking about photo, cute. Instagram also never came up before. You see? So a lot of new words have come up. People are talking about taking pictures. Okay. So a lot of new words have come up. Now, important thing is, there are some words which probably may not help you in this particular task. What is the task we are trying to do? Come on. What is the task we are trying to do? We are trying to make a machine learning model, which is essentially going to be a classifier model. Classify a tweet as positive or negative, right? Now I'm highlighting some of the words here. Come on, tell me, do you think the word like phone, calm, even the word like Twitter, word like retweet, do you think these words can determine the sentiment at all? I mean, any positive or negative tweet will have these words, right? Come on, what's your opinion? Do you think these kind of words have any sentiment? Even you can use the word phone. Where is there? Phone, I had got. Phone, mobile was there somewhere. I had seen. somewhere it was. Okay. No, right. So what I can do is I can further remove these words entering into my corpus. Okay, I can further remove these words. Okay, perfect. So let's do that. If you want, we can do that, but then you'll have to change your cleaner function once again. Okay. So I'm not going to do that. That will be given to you as your homework. Let's call it as domain specific stop words. Okay. We call normally it as domain specific stop words. Let me create a list and I'll give you that as the homework. Okay. You try it out anyway. You will get the code in the GitHub. Okay. The updated code. So what I'm doing is creating a manual list of domain specific stop words. So let's say you are talking about movie reviews. Okay. Think about you are talking about movie reviews. So in the case of movie reviews, every single movie review will have words like movie, film, actor, director, story, watch. I mean, these 5-6 words would be there in every movie review, right? So these words cannot determine the sentiment of that movie review. So the same thing, these are all domain specific stop words for movie reviews then. Okay. Whereas the words like blockbuster, the words like boring, those are discriminative words. So they are not stop words. Is that clear? Okay. The words like awesome, brilliant, the word, so those are discriminative words, right? So don't remove them. Here I am going to remove these words. That is why I'm calling it as domain specific stop words. Words like calm and then follow or whatever. Okay. So next thing what I'm going to do is I'll create my final stop words list. Let's call it as final stop words list. But I'm not going to apply this. I'll leave this for your homework. I'll just append my combined stop words with this. There was combined stop word somewhere. So I'll just copy and paste it here. Right. So, and then let me check. I might have to convert this into a list because that was a set. That was a set. And this worked. So now your homework is redefine or redo the cleaner function to include this final stop words. And maybe replot. Let's see what more comes up. Okay. Fine. So that is done. Let's go to the feature extraction now because we have to extract features, build the model now. That's the last part. Okay. Perfect. Oh, I'm sorry. So we can do one more thing. Okay, we can do one more thing. If I just go back here, my cleaner function, I'll just change it slightly. This is with stop words. And what I will do is I don't want these two words. If you notice, there were words like this. Just 2 words, IO, words like RT. So there will be several words which have a length of a single word or 2. So what I want to do is better, can we get rid of those words as well, which have a length less than 2 or less than or equal to 2. Okay. So where do I apply that? We can apply that here. Okay. So how do I do that? So let's say new text equal to, then we'll reapply this and see what comes up. And I can copy a part of this. It's very simple. And where do I change? Now this is already a list, so I don't need to split it. All I have to do is just check if the length of this token, okay, is greater than 2, then only include that token. That's it. Okay. If that token in the new text, the length is greater than 2, only then include that token. Perfect. So that should get rid of those words like RT and so on. Okay, let's verify. It's not, RT is gone, but IO is still there. Maybe there might be a space or something. For that reason, it is still there. But most of the 2 or less have gone, right? So let's see the total length. How many words you have in your all words by now? So how many words I have is, oh, sorry, this is all the 85,000. This is not helpful. We'll see the unique words. So how do you get the unique words? Okay. So for that, we can use the bag of words model. Okay. So what is bag of words model? Basically, I want to convert my unstructured tweets. How are your tweets looking? These are how your tweets are looking as of now, right? I want to convert my unstructured tweets. Why are they unstructured? Because each tweet contains different length of words, different length of characters. So each tweet was supposed to be having same number of rows and columns. I mean, so that's what a structured data or tabular data is all about, right? So whole idea is, can I convert this unstructured text into a, tabular format, and that is done by your bag of words model. Okay, so normally there are 2 types of bag of words model that we use. One is count vectorizer. Let me give a note here. Vectorizer, and the other is TF IDF vectorizer. I'll give you a quick idea about these 2. Okay, don't worry. So what do we need? If you want, you can drop this tweet also by now, because that's not going to be helpful at all. Or if you want to keep it, it is up to you. So let me see the shape of the data. So 4 columns, 7920 entries are there. Fine. Now let me apply the count vectorizer. So what is count vectorizer? Maybe I can give you a small idea here. Okay. Right. So bag of words, maybe I'll give you a quick idea here. Okay. So what I'm taking 2 words here. Okay. Just have a look. Okay. I have 2 words. Sorry, 2 documents. I have 2 documents. One document is I love cooking. The other document is today I cooked tasty pasta today. Fine. Now there are multiple modes. There are typical 4 modes. One is binary mode, count mode, TF-IDF mode, and frequency mode. So in the binary mode, normally I mark the presence of a word from the vocabulary. So first you have to create the vocabulary. Okay. And then you have to check each word from the vocabulary if it is present in your document. If it is present in the document, then you will mark it as 1. If the word from the vocabulary is not present in the document, you will mark it as 0. Fine. So these are all the words present in your vocabulary. So I have just taken out all the words. Here I have not done lemmatization, which is the reason I am having cooking and cooked together. Okay. Otherwise, if you had done lemmatization, you would have not got these 2 different words. Okay. So, I mean, just for the sake. So now in the document 1, do you have I? Yes, I have I. Do you have love? Yes, I have love. Okay. In the first document, do you have the word cooking? Yes, I have cooking. But these 4 words, cooked, pasta, and today, they are not present. So they are all zeros. So 0 against cooked, 0 against pasta, and 0 against today. Okay. Question mark, I'll talk about in the end. The second document on the other hand, somewhere has a I, somewhere has a I. So this is still one, but the second document does not have love. Second document does not have cooking, but has cooked, has pasta, and also has today. Okay, so that is the thing. Now this represents those words in the document which are present in the vocabulary, which are not present in the vocabulary. So there could be some words in your document which is not a part of the vocabulary. Why? Because you have got rid of the stop words. There could be a lot of stop words present in the document, but not in the vocabulary. So all those words will be encoded with a question mark. That's it. So now if you see, I was easily able to encode the first document. Listen to me carefully. I was able to represent my first document into a vector of the length 1 cross 7. Another document was also able to encode it into another vector of 1 cross 7. This is called as vectorization of the document. This is called as document vectorization. And this document vectorization is the process where you are not just doing feature engineering, but you are converting your unstructured document into a structured format. Now, if I repeat this for 7,920 tweets, what will happen? I'll get 7,920 vectors. Each vector has the same number of zeros and ones. Okay. So that's how you can convert that. So just imagine that you have, so the length of each document vector is always equal to the total number of words in the vocabulary, right? So what I am going to get is N cross P, where P is equal to the number of words in the vocabulary, right? Your final feature matrix. This is my final feature matrix, or what we also call as document term matrix. Okay, this X will be your document term matrix, which essentially encodes which document has which words. That is why it is a document term matrix. And this will have a dimensionality of N cross P, where P is the total number of words. N is the number of documents. And P is the number of unique words in the vocabulary. So this is my document term matrix, which we are going to construct. In the count vectorizer, what you are going to do is you are going to retain the count of the word from the vocabulary. For example, here, so what is the difference this time? This is same, but the difference will come here. Can you see the word? The word today came 2 times. The word today came 2 times in the second document. So in the first case, where we are only marking the presence, here I am marking the count. That is what exactly the count vectorizer does. That is exactly what the count vectorizer does. So here you have 2. So the same vector, but you have 2 here. Fine. And then you have the frequency model, which is nothing but your normalized count. And then you have the TF-IDF mode, which gives you the TF-IDF score. So we'll talk about the TF-IDF, but let's implement this, okay, quickly. Okay, half an hour is also gone. Maybe I'll take another 15-20 minutes, because we need to convert this and at least make a simple machine learning model. So what I'm going to do is from sklearn.feature extraction. So boring. sklearn count vectorizer. This is what we should do, or rather I do. Copy this, paste it here, put a from here, and import here. Okay. This is intelligent coding. Now, count vectorizer is a class. Please understand, this is a class. So we have to create an instance of that class. We have to create an instance of that class. Okay, remember, you have to create an instance before you could use it. Okay, so let's call it as CV count vectorizer class. I'll take the default options for now, and then I'm going to fit my vectorizer. So fit underscore transform my data, and which one do I want to use? I want to use with the stopwords or without the stopwords. I will use without the stopwords. Let's see what happens. So I'll use the one with the, sorry, without the stopwords. And then let's call this as CV features. Let me look at this CV features. Okay. And let's check the shape. CV features dot shape. Okay, so your count vectorizer has been able to make a vocabulary of 15,955 words. Okay, this contains stopwords. Okay, so if you want to apply the stopwords, I'll show you. You can apply the stopwords later also. Okay. There is a question here somewhere. Count vectorizer gets the frequency. No. Yeah, frequency, yes. So that is what I discussed. It will retain the count of how many times a given word appears in a document. Okay. Count vectorizer is roughly similar to one-hot encoding. Yes, more or less. But it retains the count. One-hot encoding is your binary mode, which I talked about. Binary mode only retains whether a word is present or not. That is exactly one-hot encoding. How many times that word is appearing in a given document? That is what the count vectorizer does. Additional information. Hope that is clear, right? Okay. Now I'll show you something interesting. Okay. I want to visualize the first feature. How does it look? This says it is a sparse matrix. It's a sparse. What is a sparse matrix? It's a sparse matrix is the matrix which contains huge number of zeros. Okay. Majority of the data points in this are actually zeros. Let me tell you. Okay. Majority of the data points in this are actually zeros. Okay. Okay, so we already have that. Sorry, I didn't see. We already had that code. So let me directly get to that point. This we already did. If you want, you can save your data. For now, I'll just skip it. This was already done. So let me just delete this. So seeing the data type here, it's a compressed sparse row matrix. It's a compressed sparse row matrix. Okay. Now, once you convert that into a dense format, you can actually see the zeros and ones. What I have done here is, after converting into a dense format, I'm dumping it into a data frame. And you can see hardly there is any one. I mean, that's exactly what I meant by saying sparse matrix. In the sparse matrix, most of the entries are zeros. Most of the entries. And you will be astonished how many numbers are present in your matrix. Can you see the size of your matrix? 126 million entries are present. 126 million entries. Entries means each of them is an entry. So the size will give you how many, and I have divided by 1 million here. So 126 million numbers are present in your matrix. This matrix is your document term matrix. This is your document term matrix, whatever I was telling you some time back. A document term matrix, that's exactly how it looks somewhere. So this is your document term matrix. Let me just put it here. Okay. Contains 126 million entries. Now, interesting thing. Let me count how many non-zero elements are present. So only 114,000 non-zero elements are present out of 126 million. So what is that ratio? That ratio is 0.09%. I've already multiplied by 100, you see. So this is the percent of non-zero elements present in your data set. Oh my God. So I have got a huge matrix in which not even 0.1%, forget about 1%, not even 0.1% data is non-zero. So 99.99% of this matrix is containing zeros. 99.99% of this matrix is containing zeros. Are you able to feel what this is? This is completely mind-boggling for a machine. You are feeding this data to a machine which contains 99.99% zeros. What is the machine supposed to learn? For a human, it's impossible. You cannot even think about it, but at least machine will still try to learn something. Okay, so that is the beauty of machine learning. Your machine will still be able to learn something out of it. Okay, so that is the beauty. So let's see what we have got. You have got these kind of words also. You see, Alborg is a name of a company, so I know that. But these kind of words are also there. You see, these kind of thanks, abuses, expressions. Yeah, you see. So a lot of these words are present. This is Abu Dhabi, sorry. But you see very easily that these are the words coming from your vocabulary. Okay, so these are the vocabulary words. Okay, and how many vocabulary words are present now? 15,955. This is the number of vocabulary words. Okay, and you are actually able to see the vocabulary. And who is extracting? Who is constructing the vocabulary? My dear, the count vectorizer itself is doing all that hard work. We never created the vocabulary. We just gave the data frame, transformed it. Okay, you see, we just fed the data frame, transformed it. And automatically everything was generated. The vocabulary was generated. Perfect. All good till here. So see, the length is 15,955. And let's say I want to transform my numbers back to words. My numbers back to words. See, these are the numbers corresponding to, these are the numbers corresponding to the 10th tweet or 11th tweet, for example. Okay. This doesn't make any sense to a person. To a human, this is all Greek and Dutch. I don't understand these zeros and ones, let's say. So I can use the inverse transform. I can use the inverse transform idea to convert those zeros and ones into actual words. That's what this line of code is doing. So vanity remover. Perfect. Okay. So come to the model building part. Okay. So all good till here? People enjoying? I have done my customary test train split. So everyone knows, right, what a test train split is? And why do we need it? Yeah. And there is one special thing here. If you notice, there is one special thing. Can you see this stratify label? This special thing. What is this special thing? And why do we need that special thing? Come on. Give a thought. So basically, if you remember, I'll just quickly go to the first line here. Yeah, labels. Can you see? Sorry, your data set is not balanced. Your data set is not balanced. What does that mean? You don't have the equal number of zeros and ones, right? So 75% you have zeros, 25% you have ones. Now, while doing the test train split, you want to make sure that the same ratio is maintained in both the training and the test set. How do you make sure? And that is what the stratify option does. So stratify option makes sure that you are going to make two parts of your data set, right? One part is your training set one part is your test set, correct? So both the training set and the test set have the same fraction of zeros and ones. To just make sure of that, we are using the stratify option. Clear? I want to use logistic regression. So logistic regression, sklearn. So from scikit-learn.linear model, just copy and paste that. Import logistic regression. Very good. And if you want, you can import the logistic regression. Okay, I have done some penalty here, but let me try it out without doing that. Okay. So obviously, I need to run the logistic regression with the default options and see what happens. Okay. Just using all the default options. So I'm creating an instance of the logistic regression model. Okay, let me call it as simply LR. LR is your logistic regression model instance. Solver, I'm changing to liblinear. It's a bit faster and mostly works. Okay. Since your dimensionality is huge, you need a faster option. Okay. Then what? You are fitting it on the training set and getting the model's performance on the test set. Okay. Let's see what we. So we have got 97% on the training set and 88% on the test set. I'll pause here for 15 seconds and I would watch out the chat box for your comments. What do we infer out of this? Okay, some people are saying very good. Is there anyone who says very bad?
Could this be a overfitting as well?
Could this be overfitting? Okay. Okay, very good.
Because 97% could be a overfitting, 97%. I may be wrong, but
okay, very good, very good. So I just want to modify your statement. Remove that could be. It is overfitting. 110%. It is overfitting. Your model is basically screwed up. Okay, this is completely, not a model which I would ever deploy. Fine, your model might be giving 98% accuracy in the training set, but this is useless. I would never have confidence in such a model because of this huge gap, of training and test accuracies. Typically 1 to 2% is acceptable. Please listen to me carefully. Model building is easy. 3 lines of code. You have built your model. I am done for the day, for example. But the interpretation of the results takes another data. Okay. This model is completely useless. Should not be deployed. It might give you the best accuracy. Let me, be very, very clear. Okay. But this is one of the most useless models. You cannot deploy this model. You cannot deliver this to the client. This model might be good to win a Kaggle competition. That's okay. No one is caring about that. No one is anyway deploying your Kaggle model anyway. But such a model is highly unreliable. So that is the biggest problem with overfitting. If the training and test gap is huge, your model is not reliable and it will give you inconsistent performance. Now, 2 questions arise out of it. How do I check the consistency of my model? How can I make sure that if the client comes up with a similar test set after a month, can I guarantee him that I'll get same 88% accuracy? Can you do that? Is that possible? So answer is clearly no. As of now, no. As of now, no. So someone mentioned about cross-validation. Manju, absolutely. So cross-validation is the technique which you use to make sure, or to figure out the consistency of model's performance. So we'll do that in the next block of code. And the second question is, of course, is this much difference of training and test accuracy is acceptable? Answer is clearly no. So this is the best way you can get whether your model is overfitted or not. So the point I'm trying to hint here is, even simplest model like logistic regression can be overfitted. So people normally think that a support vector machine will give you a overfitted model. Decision tree, definitely one of the best overfitters planet Earth can ever have. Okay, without doing anything fancy, most of the times your decision tree models you will get in hand would be by default overfitted. So decision trees are best overfitters, I would say. But normally, high bias models like logistic regression was not expected to be overfitting like this. But in this case, I have a highly overfitted logistic regression model, which is slightly strange. But if you think about the reason, it will not appear to be strange. Now I'm asking you guys, what could be a reason that this logistic regression overfitted? Give a thought. Because logistic regression is not known to be overfitting so easily. It's a high bias model, will have low variance. You have heard about bias variance trade-off, right? So high bias models make a lot of assumptions. If you have a lot of assumptions, typically the model will be consistent. So some people are saying unbalanced data. Some people are talking about sparsity. Some are talking about statistical matter. I couldn't understand that statement. Prashant is saying less features. Is it less features? 16,000 you have, man. How many more you want?
I would go with sparsity.
Sparsity could be, okay. See, the simplest answer is, so you have a simple problem. I'll try to, rephrase the question. Suppose you have two variables, simple, X and Y. And I give you 10 equations in those two variables. So if you have two equations and two variables, you can get the unique value of X and Y. Everyone has done this in their high school. Come on, tell me yes or no. Everyone solve 2x plus 3y equal to 5, 5x minus 6y equal to 10. If I want to find out the value of X and Y, I'll be able to get this. But if I have two equations, listen to me carefully. If you have two variables, and 20 equations, what will happen? You are confused which two to take.
Yes.
Two to take, exactly. You only want two. That's the problem the machine is facing right now. You have more than the required information. This excessive number of features is the root cause of this overfitting, nothing else. Sparsity is not a problem. This excessive number of features is the actual problem here. So what it is hinting is, you didn't need 16,000 features probably. Let's narrow down. To maybe 1,000 features, 2,000 features. That will give us a better model. How do you do that? So then what I thought was, okay, let's do regularization. Everyone knows L1 regularization, L2 regularization. L1 is lasso, L2 is ridge. L1 is used when you want built-in feature selection, correct? And L2, which is ridge, that is normally used when you have multi-collinearity problem in your data set, correct? When you have multi-collinearity problem in your data set, then you would go for L2 regularization, which is ridge. Right now, what I'm going to use is lasso, which is L1 penalty. And after some trial and error, I found 0.5 is best. You might do hyperparameter tuning, grid search, and all that stuff. That's up to you, okay? Fine. So let me quickly, sorry, let me quickly run this code with penalty parameter of 0.5 and see what we get. So I'm still getting 91 and 88. See, this is pretty close. This is what I wanted. Beautiful, beautiful. This is what I wanted. Let me try to make it 0.6. Awesome. Okay, let me make it 0.4. Slight tuning. Fantastic, man. This is the best what I wanted. I mean, it cannot get better than this. 90% in training, 88% in testing. Perfect. This is the ideal scenario. Is this clear to everyone? Yes or no? Okay, so this is the ideal scenario. Now you have a non-overfitted model. This is the best model. And there is a slight compromise in the accuracy. No, not yet. 8.13, this is also giving you the similar. So you see, now you have a less overfitted model. Definitely you have a less overfitted model. So normally this can go down. This goes down. I'm also surprised why is this number not going down. I'm actually surprised why is this not going down. Okay. I tried using L2 and all that, but that did not help. So if you want to keep it, you can keep it or you can delete it. That's up to you. But I did check L2 penalty. That was not giving much better result. So I'll stick with L1. Okay. Now let's quickly cross-validate how much code we have left. Okay, I'll probably leave the remaining part after grid search. Okay. So 2-3 more lines of code and then the remaining for yourself. Okay. Okay, so can I quickly cross-validate my model? Okay. So I'm importing my cross-validation function, CV features in X, label in Y, perfect, and cross-validate my LR1 model. Okay. So what will I do? This code was supposed to come. So I actually built multiple models and I just, okay. I'll use L1 and what was the value? 0.4. So I'll go ahead and change it to 0.4. Number of splits, and here also stratified keyfold if you see. Okay, because so in the 5-fold cross validation, what is going to happen is you are going to split your entire data set into 5 parts. 4 parts will be used for training, 1 part will be used for testing, and you repeat the same 5 times. Okay, each part, the test set will be different. So that's how it works. And you are extracting the cross validation score here. Let me just print the results now. Here I have got 88.28% is my cross validation accuracy, the mean value, mean cross validation accuracy, and 0.93% is my standard deviation, which now tells you that your model's accuracy should be reported as 88.23 plus minus 0.93%. Now I've got a better confidence. I know that in the worst case, it is 88.23 minus 0.93, and the best case, it will be plus of that. So that much variation I can have. Can you see the numbers? So it is down up to 86.9 and it can be up to 0.897 also. So slightly less or more. How much less or more? That is given by your standard deviation. This standard deviation should be small, and smaller the standard deviation, better is the precision of your model. Okay, so precision can be obtained only when you cross-validate your model. Is that clear? So if you also want to have your training accuracies, then you would need to go for cross-validate function. See, this is your cross-validate function, and earlier I used cross-validation score. The beauty of cross-validate function is it can return the training scores. Can you see? It can return the training scores. Now I'm going to print the training scores as well. Let's see how it works. So you see, you have the training scores and you have the test scores. What I'm going to do is just take the mean of both and see what I get now. So this is the mean of training scores, 90%, and the mean of test scores, which is 88%. The standard deviation of training score is 0.2, and the standard deviation of my test scores is 0.93. But these are percentages, okay, because I've multiplied every time. You can just multiply. So this is pretty good. Like, man, I am very happy. Okay, but the only problem is you have huge number of features, and we narrow it down. If you want, you can do a grid search, and this time I am searching on the values for. This is for the penalty L2. You can, so maybe if you want, you can do that, or you want to skip this. Let me skip this, or I'll just keep it. Maybe if you want to do that. L1, and you can change some of these values and see which best value you can get. So I'm not running this. This might take some time, and then you can see. So this is all just printing the grid search results. Everyone knows how to do that. So once that is done, I'll just print it. Let me go ahead. Just simply printing the grid search result. Don't worry. Finally, I'll create a pipeline. Why do I want to create a pipeline? What is the criteria to choose penalty? I've already mentioned. L1 penalty is used when you want to reduce the number of features. If you want to have feature selection built in. Okay. And here we have 16,000 features. So I indeed wanted to choose the important features, right? So I've got my candidates fitted. These are the results from grid search. This is the best value. Let me see the parameter value. 0.95 is the best parameter value. And I wanted to show you something here before I wanted to. I want to go ahead. Let me show you something interesting. Something interesting. And this, I'm 210% sure you might have never seen this kind of thing. Okay. I've simply plotted the difference between training scores and the test scores here with respect to the C values. Okay. These are the C values. Sorry, indices. These indices can be converted into C value. Don't worry. This is the 0 to 20 index, and the C values are actually mentioned here. Okay. Listen to me very carefully. I'm discussing something very interesting. As per grid search, my best value is 0.95001. Okay. Listen to me very carefully. As per the grid search, the best value is 0.95001. And for this value, the test accuracy, the best test accuracy is 0.89. Now, I am very, very sure that everyone would think, awesome. I was able to get the accuracy from 88% to 89%. Is it not? See, when I did a manual grid search, what was my value? 88.28. Is it not? 88.28. This was on the test data set, correct? See here, 88.28. Perfect. Almost everyone will think that I've got a model which is having a better accuracy. 0.89 is definitely better than 88.28. Yes or no? Come on. Comment in the chat box and tell me. Is 89% better than 88.28? So are you happy with the grid search results? This is what everyone does, right? Blindly. I shouldn't be using that word blindly. But this is what everyone wants, right? You want to use grid search to find out the best model after hyperparameter tuning. Of course, the improvement in accuracy is not drastic. That was not even expected for a logistic regression. For nonlinear models like decision trees, SVM, the improvement will be drastic. Okay. But for linear models, this improvement was not even expected to be drastic. But at least there is an improvement. I've got a better model. This is what everyone thinks. You are fooling yourself. Why? Let's see. This is the mean test accuracy. And this is the mean training accuracy. What has happened? Do you see? Yeah. So the standard deviation and the results mean tensor score thing. So yeah. So just focus. I'm just highlighting something. Please pay attention here. 89 is your test accuracy, okay, mean test score, and 93.27 is your mean training score. My dear, that difference, I was very happy some time back, right? I was very happy some time back that I've got a non-overfitted model. This grid search has given you a grossly, come on, complete the statement. This grid search has given you a grossly, complete the statement, overfitted model. So if you blindly trust the results of grid search, these are the problems. So you would go ahead and definitely upload this in your Kaggle. This has much higher accuracy than the previous one, but this is more useless than the previous one. At least the previous one was much consistent. Here, I mean, you can see the standard deviations, my dear. It was 0.2. It was 0.2. And now that 0.2 has increased to 0.64. The standard deviation increased from 0.2 to 0.64. See, if the standard deviation increases 3 times, the variance increases 9 times. So my model's variance, I mean the prediction inconsistencies increase exponentially. So not only this model is overfitted, but also the other challenges of not being reliable also increases, right? Is there a way to measure overfitting? This comes by experience. I mean, but these are the numbers. That's why you should, dissect, do a postmortem of every single step. Don't blindly go with the gross numbers. How many of you have dissected a grid search result to this extent? Right? So you want to know the difference between the accuracy between the training and a grid search doesn't take out that into account. Okay, so I think you get the point, right? I was very happy some time back that I have got a very good model. Yes, indeed, it's a very good model, but my grid search best model is, my dear, overfitted. This is as simple as that. So don't blindly trust your grid search. Okay, that is why a manual human intervention is needed. That is why AI is not going to replace humans. Whatever automated auto ML might come, they cannot replace Prashant. They cannot replace you. I cannot take down the names. They cannot replace Edward, Mayur, Ashwin, Keys, and everyone else, right? Auto ML can only give you something, but a human is needed to make sense out of those numbers, interpret them correctly, choose the right model, deploy the right model. Right model is not the model every time which is having the highest accuracy. So don't be so desperate. Think logically, not desperately. Okay, so these are the skills which come by experience. The Udemy learned data scientist, the self-learned, these misconceptions come automatically, unfortunately. Okay. I mean, I can keep on going, but there we have to stop somewhere, right? So there is a pipeline which I created. Let me check if I can quickly say this pipeline. So I'll go back to my point 4. Use L1. And what else? I run this pipeline quickly. So do I have the clean tweets? No, I do not have the clean tweets. I have the clean tweets with stopwords. I've created a pipeline.
I guess the name was different.
No. I think What is the error coming? Clean tweets with stopwords is not present. Okay, just a minute. There was some X I had defined. I probably overwritten that. Okay. No, so I don't want this. Where is my data head? I wanted my data head. Okay. So I'll just copy this last part. Sorry, this one. Clean tweets without stopwords. Sorry. Without stopwords. I'll use the one without stopwords, and I'll tell you the reason why. Very simple. Okay, so this is how your pipeline looks. Just printing the pipeline here. It doesn't print. These are the named steps, and I'm extracting your, so this is your pipeline. This is a pipeline. And what did I do in the pipeline? The first step is your count vectorizer. Second step is your logistic regression. I think that's very simple to understand, correct? First step. So I'm feeding my raw data directly to the pipeline. So in the first step of the pipeline, this count vectorizer will create the vocabulary and extract the features, transform your data set from unstructured to structured. Features would be created, and those features will be automatically passed to your logistic regression. Simple. And now I get the same result. So this was not surprising. This was very much the same result, 88.28, but this time using pipeline. That's it. Okay, perfect. I'll tell you a reason why I'm doing this. Okay. So this is my pipeline, and you can see the same 50,955. This is how you can extract the vocabulary. Perfect. This is the reason. So one reason is you can see the words and their frequencies, which we never saw till now. Okay, this is exactly your vocabulary, man. This is what I was telling you every time. Your vocabulary would be a dictionary. Yes, this is my vocabulary, right? With all the 15,955 words. This is your vocabulary. Next. What I am going to do is just copy. And I'm going to create a model without the stopwords. Okay, quickly. Just paste it here and without the stopwords. So this time what I'm going to do is, please pay attention. This count vectorizer, my function is there. Can you see here? Can you see here? There is a stopwords option. I'm going to use that. I'm going to use that. Quickly. Stopwords, copy that, come, paste it here, and you had the final stopwords. Pass it here. Pass it here. So you started with a data set where stopwords was not removed, but you can use the count vectorizer and apply the stopwords before the vocabulary is created. That is the beauty. So even applying stopwords can become a part of the pipeline. See, applying stopwords can also become a part of the pipeline. So now you are getting a machine learning model after applying the stopwords. And what do you find? What do you find? My model has got a lower accuracy. Now you get the point why I was not removing the stopwords. We initially thought that stopwords are going to be useless to the model. In fact, they are not so useless. You can see 88% dropped down to 86%. So now it's your choice whether you want to retain the stopwords or not. At least we have a comparison. We have a fair enough comparison. Is it not? At least we have a fair enough comparison. So try creating a model without doing exotic transformations. A bare simple model with all the words without the stopword removal, I can very easily remove the stopwords. And let me give you one more simple thing. Okay. This time, not only I'm going to remove the stopwords, but please pay attention. Another 2 minutes, just 2 minutes. Okay. I'm going to use these two, min df and max features. Okay. See what happens now. Min df, I'll make it 10. And let this be same. Okay. Let's see what happens now. I'll tell you what has happened now. I've got a model where you have accepted only those words to be a part of the vocabulary. Listen to me carefully. You have got a model where you are accepting only those words to be a part of the vocabulary where or those words which have a minimum document frequency, of 10. What does that mean? That any word which is present in less than 10 documents will not be a part of my vocabulary. So your vocabulary is narrowed. Now see what happens. Let me print the vocabulary. Let me print the vocabulary. Okay. Let me print the vocabulary and show you. Okay. You have only 1086. And in the previous case, you have, let make it part of the code itself so that it will avoid confusion. Sorry. You have 15,673 after applying the stopwords. So how many? Only by removing, you see, only by removing roughly 300 words. Only by removing roughly 300 words, the accuracy dropped by 2%. But then something astonishing happens. Okay, listen to me carefully. Dropping these 300 words, which are stop words, gave a compromise of 2%, easily 2%. But dropping it further from 15,000 to just 1,000, there is hardly any compromise. You see, what does that mean now? The remaining 14,000 words were not contributing to the model. I mean, this is the best model. So if I am supposed to choose which one to deploy, I'll actually probably choose this one. Not even with the stop words, not that 89%, definitely not. Not that even 88% with the stop words, not that with 15,000 features. I'll choose this one with only 1,000 features. And let me show you one last another beauty of that. Can I make this as 1,000? Okay, listen to me carefully. I'm making it 1,000. So what is happening this time? I'm choosing only 1,000 features to build a model. And did the accuracy drop? Actually, 86.77? No, there is no compromise in the accuracy. Okay, so this model is probably the best model. With only 1,000 features, you have a decent enough accuracy, 2%, that's very fine. But see, the advantage of having these 1,000 features is these 1,000 words would be present in almost every tweet, which are not stop words, of course, because I have removed the stop words. And this is a more generic model, a generalized model. Okay, this is a more generalized model, and this model will not only train faster but also give you predictions faster. Why will it give you faster predictions? Come on, because you don't have to extract all the 16,000 features. You don't have to extract 16,000 features. This model is only working with 1,000 features. So this is going to give you more real-time, near real-time predictions. That model will give you 15 times slower prediction. 15 times slower prediction. This is the one which will give you 15 times faster prediction. At what cost? Just 1 to 2% accuracy. Fine, that's fine. So we have to think practically, not emotionally or desperately. That's it for today. Thank you guys for bearing me for more than 2.5 hours. I'm all yours. I'll upload this in my GitHub once again at the end of the session. And the feedback poll is already there. And yes, I can see your feedback. Okay, so everyone has responded pretty well for my session. Thank you. Thank you so much. And maybe I'll take a few questions because I know there have been people who have been patient enough for 2 long hours waiting for their doubts to be cleared. So I'll not do injustice. I'll take at least the most important questions. Okay. So
Yes, it was worth it.
okay. Thank you. Thank you. So I mean, you'll have to rename data couple of hours instead of data hours. Let's start another series, data couple of hours or couple of data hours. Maybe
Yeah,
that.
you are the manager. You can do that, obviously.
I know. No, I'm not the data manager. I'm not the product manager here. I just take trainings, that's it. So there are different people who make those decisions. So I'm not the right guy. So anyway, it was just a joke anyway. So I don't want you to take it that seriously anyway. Okay, perfect. So I'll just open my Q&A and see some of the questions. Please give me another 5 minutes. I'll just take some of the very important questions. Okay, so Merlin had asked, I'm answering that question live. So my questions are related to how do you get this data set? So of course, you have to go for TWEPy, TWEPy. TWEPy is the package. Please download that TWEPy. Get your Twitter API credentials. Use this API and download. So all you have to give is a hashtag and you will be able to download. There is a fair usage limit policy, FUP they call. So they have rate limits, but you can give your, hashtags and download tweets as per those hashtags. For this particular Twitter, that was your answer. And Piyush is asking one question. It is not related to sentiment analysis, but NLP. How can we calculate sentence similarity using transformer? That will be taken in exactly the next session. Sentence similarity, word to vec, global vectors. Corpus versus concept net. Okay, this is not the right platform to discuss. I mean, that would be too technical to discuss, Ashwin, sorry. You can easily get that answer in ChatGPT. I'm 210% sure. Okay. Okay. What else? Some anonymous attendee has asked, will there be a session on building the data set for the sentiment analysis? No, unfortunately not. Maybe if there is a lot of requests, I might think of, but not yet. I haven't planned it as yet, frankly. Okay. There can be definitely. I'll just put this in the requirement if someone can take it. Shravanti is asking, so we need to clean the data for all data points. We have taken, yes. So we have done data cleaning, definitely. Okay. Mohammed Soyab is asking, sir, how to classify sentences positive or negative? Suppose I don't have the labels, you have to do the manual labeling. There's no other way. Okay, so you have to do data labeling by yourself. That's the best, or you can use some document clustering algorithms. But then please understand that those unsupervised learning techniques will have a lot of errors. Okay, so worst case scenario, if you have 20 million documents and you do not have enough time, resources, and bandwidth to do it manually, there is AWS services available. Okay, there are a lot of third-party companies registered on AWS. You can upload your data set to those services. They will charge you like 0.02 dollars or roughly 1 or 2 cents per document to manually label it. Okay, so they will do. So third-party manual labeling services are available. So that's the best for a startup or any large-scale company. So unless you have a manually labeled data set, so ultimately, otherwise you will be teaching wrong concept to a machine. So machine will learn something wrong and it will consistently keep predicting wrong. And then you keep wondering and pondering what wrong is happening. Arey bhai, the wrong thing is your data set itself. Okay, so spend time in your data set, cleaning, getting the right data set and everything else. What else? A notebook is shared, Prashant. Share the links for sentiment analysis on audio data. That is a bit out of context. Audio data, there are several other things actually. It's a spectrum, frequency spectrum. So a lot of signal processing concepts are needed, not related to NLP. So a different level of answer is needed. You will require a lot of filters, high pass, band pass filters. So to get rid of the noise in that data, independent component analysis, maybe to get the noise out of that audio data and so on. So, what else? One is asking, why are we taking top 25 words from the unclean data set and not clean. I did both, so fine. And Shravanti is asking that regex. Fine, I think I have already explained. Himanshu is asking, sir, is there any way where I can learn it from scratch? So there are, previous sessions, all the previous sessions, data sessions are there, the recordings are there. Please go to the YouTube. I think the links have already been posted several times. So it's all there. Shittu is asking, does it mean it's advisable to have the frequency plot so that, okay, now I want you to do this homework. Instead of count vectorizer, please try out TF-IDF. Okay, in the next session, I'll explain you what is TF-IDF. Okay, if you are attending my next session, I'll explain you. But if you already know it, please apply the TF-IDF vectorizer instead of count vectorizer and see the comparison, right? See the comparison. So where do you apply? In the pipeline. Don't do it elsewhere. That won't make any sense. Okay, the pipeline. So change the pipeline, change this count vectorizer with TF-IDF and see what is the difference. And you tell me which is better for this data set next time. Okay, I'll explain the inner workings and the calculations in my next session. Promise. Okay, what else? Code is already shared. What is dense format? Okay, see, sparse and dense, they are antonyms of each other. Fine. So dense is where everything will be a number, even if it is zero. So in the sparse representation, please note that zeros will occupy much less memory compared to any other non-zero number. So that's how the compression starts. So the machine will compress all the zeros. Zeros will not be represented as float zero or integer zero. It will be in a compressed format so that zeros will take literally 1/10 the memory. So now if you have 99.99% of the matrix as zeros, and if you compress all those zeros, the memory which is taken by your CSR matrix will be much small. That was the whole idea creating your CSR matrix. Okay, but the biggest problem is your machine learning algorithms don't work with CSR data. I'll show you, not even your PCA sklearn. If you search, someone pointed, can we do dimensionality reduction? My dear, I'm sorry. Clearly tells you that PCA does not support sparse. So you have to convert into dense. So you need to get the features in numeric format. Otherwise, you cannot even run PCA. So there is an option, you can try doing SVD. So maybe we'll try that SVD in the next session and compare. Okay. So PCA also will not work on your sparse input. So these are the problems. Can we use max features? Yes, we have used that. So I think most of the questions are answered. Mayur is asking something about SMOT. So SMOT is synthetic minority oversampling technique. So see, I have said it very clearly. Here, my intention is not to discuss more about all the techniques which are available for the entire machine learning workflow. How you can get started with a textual data, clean it, build the features, build a model, and most importantly, test the model in a logical way, not in a desperative way. Okay, so that was the whole takeaway from this. And now each model, each algorithm, we can dig down, each step, feature selection, everything we can dig down. Okay, someone would say, why did you not do feature scaling? You could have tried actually. After CV, please try this. Put a standard scaler here before you feed it to your logistic regression. Try what is the difference. Okay, put a standard scaler here. Okay, and see what is the difference and tell me. So you can even try rescaling your data or standardizing your data for logistic regression, because logistic regression assumes your features have Gaussian distribution. So standardizing might help. Okay, so a lot of several things, these things can be done, no doubt. Murtaza is asking, what is the evidence of overfitting? We have discussed this several times. The difference between training and test set cannot be huge, not more than 2 or 3% ideally. Okay. Acha, so what if, let's say, your training score is 49% and test score is 48%? What do you call? Is it an overfitted model? Come on, tell me. Those people who are still there in the session. If my training score is 49% and test score is 48%, is that an overfitted model?
No.
Okay, very good. It's not an overfitted model. If your training score is 49% and your test score is 35%, then?
Yes.
Yes. Okay. Now I have a difference of opinion. So listen to me carefully. In both the case, it could be a underfitted model. See, both are struggling. Okay. The training score and the test score both are struggling. Right. So in the other case, it's not overfitting. In the other case where you said that 49 and 35, no, it's not overfitting. It's still probably underfitting. So underfitting is when the model is not able to learn the pattern in the data set. If it has not learned, how do you think it will be able to give the predictions in the test set? As simple as that. So having a very small training and test accuracy also indicates that your model is grossly underfitted rather than overfitted. So that angle also you should have a look. Okay.
So like what's the best score should we as an beginner, what's the best score we should look for?
Best metric are
I
you
mean,
talking?
yeah, I mean, give me a range or window of scores so that we look for.
So that's pretty tricky because it will completely depend on data set to data set. So there has to be some benchmark cases. Okay. There has to be some benchmark cases and benchmark models. So for example, if you are doing regular modeling on a similar kind of data set, you know what are the typical accuracies other people are getting. If everyone is getting 85, 86% and you are still struggling at 49, 50%, means you can't even imagine overfitting in such a case, man. It is grossly underfitting. Now, if you're close to their numbers, 85, 86%, but the test is still lagging at 68, 70%, then it could be a case of overfitting. Or you have exceeded 95%, but the test is lagging at 80 or 85%. That is again a case of overfitting. So if you have got a decent enough accuracy, but the difference is huge between the training and test, then it indicates overfitting. I mean, there are several ways. The other way is cross-validation, accuracy and the mean. So if the, not the mean, standard deviation. If the standard deviation is very large, if it is more than 3%, 5%, you will normally see in decision trees, it goes to 10%, 15% also. Simple Titanic data set, if you apply decision trees, let me tell you, it gives you a variation, standard deviation of 15%. I actually remember the numbers. The training accuracy is 100% or 99.9, and the test accuracy is 0.74, basically 74%. So 74% against 100%. That is a simple decision tree. It's a grossly overfitted model, right? So if both the numbers are struggling, that could be hinting underfitting. And if at least the training accuracy has exceeded a decent level, 85, 90%, then you expect your test to be at least closer to that number, right? If it is still lagging far behind, that's overfitting then.
Yeah, got your point.
Okay, thank you guys. Thank you guys. So I am done. You can reach out to me. So most of the questions already taken.
Yeah. So thanks a lot, Prashant, on behalf of Analytics Vidya. I would like to thank you for your time and delivering such a wonderful session. I'm sure the audience found it insightful, and hopefully we can conduct more sessions with you. And like, I would like to request Analytics Vidya to tag me with you for the next session as well.
Yeah.
If you are hearing Analytics Vidya.
Okay, so
thanks.
that's not under my control, so don't request me. Okay. Thank you so much. Thank you. Sorry, I forgot your name.
Yeah, that's Deep Prasad. Okay,
Deep,
thank
Deep.
you, sir.
Thank you, Deep. Thank you, Deep.
Yeah. Okay. Thank you, sir.
Thank you, guys.
Yeah. Bye, everyone.
Bye. Bye-bye.